Today we're going to be learning about velocity and doing some simple calculations to calculate it. We're also going to go a bit into how the units work for the specific calculation and try to understand the relationship between them. So let's say we have a graph of velocity. Uh, no, a graph x and y. X and y. We're going to label the x position time. Let's make that a bit smaller. X position is going to be time, and the y position is going to be position. So that's going to be the y-axis, and this is going to be the x-axis. Origin is going to be 0. This graph is going to help us understand the formula for velocity a bit better. This is what's known as so slow this a bit down. This is what's known as a position versus time graph. Position versus time. I'll draw a position and movement through time using a straight line. So just to keep things simple as possible. So let's go with the color yellow here. It's going to be straight like that. And let's just say right here is 2 seconds. It's a bit lower. Right here it's 1 second. And then half, half. And then over here, we're going to label this one. Move this a bit to the right, just so I can have more space to label. So this position is going to be, let's do 10 meters. 10 meters. This one's going to be 5 meters. 5 meters. Oops, a bit lower. 5 meters. And it's going to be half and half. So 2.5 meters, 5 meters, 7.5 meters, 10 meters, and then it's going to be 0.5 seconds, 1 second, 1.5 seconds, then 2 seconds. All right. So now that we have this graph, we need to understand that velocity is just the rate of change of position versus time. And like, what's a rate? A rate on a graph is going to be the slope of the graph. Do you guys remember how we would find the slope of this graph? We're going to use the formula rise for run, not run, equals slope of this graph. So we know that this graph rises 10 meters. So 10 meters. We're going to keep the units again, like how we said last time. We're going to keep the units, 10 meters. And then the run of this graph, the change in x, was 2 seconds. Again, if you guys aren't familiar with what rise is, what run is, rise is how much the line rises, and how much the line runs. Okay? Equals the slope. For calculation, this is going to be slope. Again, we're going to keep the units. We can't really cancel out meters over second. We can't cancel them out, so we're going to keep it all together. But we can divide 10 by 2. So we're going to end up with 5 meters per second. So whatever this object is, throughout this entire time, it was moving 5 meters per second because we have a straight position versus time graph. All right. So our answer ends up in units of meters per second or distance versus time. Probably seen this measurement on like speed limit signs or speedometers, but in those scenarios, it's either kilometers per hour or miles per hour, which represents the same exact thing, except like they changed this meter right over here into kilometers. Kilometers. Again, it's just both are a measurement of distance, and then the second is just an hour. Same thing with miles. Miles, it's just a measurement of distance per hour. They both represent speed. So we can convert this meters per second into kilometers per hour. It just takes a bit more of a calculations. So the way this would be turned into kilometers per hour is if instead of 10 meters as the rise, we could just turn this 10 meters into kilometers. So how many meters are there in a kilometer? It's going to be a kilometer has 1,000 meters, right? So we're going to do 10 meters divided by 1,000 kilometers. Or like, I'm going to do it a bit simpler just to make it a bit easier. Per 1,000 meters, there is 1 kilometer. And then we can cancel out the m's. We end up with 1 kilometer. And then we do 10 divided by 1,000, which is 0.01 kilometer. That's how many kilometers we have. And then for seconds, we have 2 seconds. 2 seconds times how many seconds are there in 1 hour? It's 3,600 seconds. Right? So our seconds cancel out right over here. And it's going to give us a really long decimal. So I'm just going to do 2 over 1 over 1,800. And then our units for this would be hours. So we have this many hours and this many kilometers. And then what we would do is we would just do the same exact calculation as we did up here. It's going to be slope, because we're measuring the slope of this line. Slope equals, it's going to be 0.001 kilometers over 1 over 1,800 hours, which is equal to, let me just calculate this real quick, to 18 kilometers per hour. So this value and this value represent the same exact speed. They're just measured in different um, units. So instead of meters for distance, we use kilometers, and for seconds, we use hours. And the same thing goes for miles per hour. It'll be the same exact thing, just a bit different units. So for this course, we're going to stick to meters and seconds. Throughout physics, you usually do stick to meters and seconds. It's just later on, sometimes you start working with particles, sometimes you start working with something huge like planets, galaxies, and then you move on to different units. There's parsecs, astronomical units, really small microseconds, micrometers. There's it just moves on to a bunch of different units. But for this course, we're just going to stick to meters and seconds, just to make things a bit easier for us. So now that we have this calculation here, slope equals rise over run, we understand that this is the rate of change of the position, and that is the speed, right? We've now confirmed that the slope is the speed. We now have our velocity formula, which will be used for other equations as well, for other calculations as well. So v vector equals change in distance or displacement over change in time. And throughout the classical unit, we're going to be using this formula for speed calculations. There are going to be questions where you're going way, way, way faster than anything that we have currently that can go that fast, or like things that are approaching the speed of light. Right now, if you guys do know about it, we don't need to worry about relativity because we're going to stick to classical physics. So let's do some practice questions with velocity equals change in displacement over change in time. Let's say the guy is back from the previous video and he's running. He takes a jog of 50 meters and he completes this entire jog in 5 seconds. 5 seconds. So very bad sound clock. He completes this in 5 seconds. Now, how are we going to calculate the speed? that he's going. We are going to do the same thing, except instead of slope equals rise over run, we're just going to do velocity equals change in distance over change in time. The total change in distance or change in displacement is going to be, well, the total displacement, I'm not saying change in displacement, the total displacement is going to be 50 meters. So we're going to do 50 meters. And the change in time we have is 5 seconds. So how fast is he running? He's running at 10 meters per second. So let's do another question with slightly more uneven numbers. Okay, let's do, we have Guy again. And Guy is going to be running 100 meters this time. And he does this now in 14.4 seconds. So what is Guy's average velocity? So again, what's known is that we have displacement is 100 meters, and change in time, is going to be 14.4 seconds. We're going to use the same formula as last time. Velocity equals d over t, which is 100 meters. Go down here, which is 100 meters over 14.4 seconds. And again, same as last time, we're going to keep the units. We're not going to get rid of them. Keep the units. The reason we keep the units is because, like, if you do the calculation without the units, we still end up with meters per second, right? Just to it's sort of to double check if you're getting the answer right, and you'll be using it a lot more later as well. So our final answer, calculating, is 6.94 meters per second. So that is his average velocity throughout this entire time. So let's do something a bit different over here. We have Guy again, and just like the previous lesson, he decides to run 10 meters east and 5 meters west. Okay? Now, he does this in 5 seconds, and we're told in this question that we have to solve for velocity, and we also have to solve for speed. Those are really bad question marks, but we have to solve for velocity and we have to solve for speed as well. So how are we going to do this? From the previous lesson, we know that velocity is a vector and speed is not a vector, right? So for velocity, we're going to calculate velocity first. For velocity, we have to take care of displacement instead of speed, where we would use distance. For velocity, we use displacement. So what we're going to do is we're going to do same formula, v equals change in distance or displacement, or over change in time. Now, if you guys recall last lesson, our change in distance is gonna be df minus di, which is just initial and final position versus initial position. Okay. The way we could do this is basically what I'm asking you to calculate is the displacement, like how we did last time. So in last lesson, from there we knew that 10 meters east is the positive, or we're going to keep it as the positive for this east, and our west is going to be negative 0. So 10 meters plus negative 5 over, we're going to do 5 seconds. 5 seconds. So our total displacement in this is 5 meters. And our change in time was 5 seconds. Keep the units. Our final answer is 1 meter per second. And that's for velocity. Now for distance, we're just going to do total distance, which, let me make the formula first. D over T, change in time. So again, please align your equal signs, just to get in the habit of doing that. All your professors are going to be very happy, your teachers are going to be very happy, and it makes your math look a lot cleaner. So total distance, it's going to be 10 meters plus 5 meters. We're not going to worry about direction because we're working with a scalar over here. We are not working with vectors. Vectors, like velocity and displacement, we need to worry about direction. With scalars, again, we don't need to worry about direction. We could just input the magnitudes. So 10 meters plus 5 meters, we're left with 15 meters up there. And then change in time, again, is 5 seconds. 10 plus 5, 15 meters over 5 seconds. And this time, for speed, we have 3 meters per second. Our velocity is different than our speed. And that's just because how we calculated it. Our velocity is just going to be the total displacement over total time, like however much time it took. And we need to worry about directions when it comes to velocity. Velocity does have a direction. It is a vector quantity. Speed is not a vector quantity, it's a scalar quantity. So we don't need to worry about direction when it comes to any of the units. So distance, direction, right? So no distance is going to be no direction. And we're just going to do that divided by total time, which is how we ended up with a different answer than this one right here. They're two different things. This is speed, this is velocity. And that's a wrap for velocity unit. The next time I post, we're going to dive more into different kinematic equations. We're going to go over something a bit more complicated, which is going to be motion that goes like this. But yeah, if you guys have any questions, just drop it down in the comments. And if you have any practice questions, please send them to me so I can go through them with you guys and post them on TikTok or YouTube Shorts just to make things a lot easier. Yeah, thanks for watching.